So the first question says, a unit may be stated with a prefix that represents a power of 10 multiple or submultiples. Complete table 1.1 to show the name and symbol of each prefix and the corresponding power of 10 multiple or submultiple. So you've got kilo first with the symbol K and has the power 3, 10 to the raised to the power 3. Next is tera, represented by an uppercase T. They're asking you, what is the power of 10 that represents tera? Tera is 10 raised to the power 12. Now, this is something that you need to remember. The last one is 10 to the raised to the power minus 12. That's a submultiple. What does this represent? This represents pico with the symbol a lowercase p. Part B says, in the following list, underline all the units that are SI base units that cannot be further simplified into units. So ampere is an SI base unit. Coulomb, even though some students have this misconception that Coulomb is an SI base unit, but it's not. Coulomb is ampere second because Q is equals to IT. So won't underline this. Meter is an SI base unit. Newton is kilogram meters per second squared. So it's not an SI base unit. So that was simple. The first two parts, pretty easy. Part C says the potential difference V between the two ends of a uniform metal wire is given by V is equals to 4 rho Li over pi d squared, where d is the diameter of the wire, I is the current in the wire, L is the length of the wire, and rho is the resistivity of the metal. For a particular wire, the percentage uncertainties in the values of some of the above quantities are listed in table 1.2. So you've got the diameter and its uncertainty. You've got the current along with its uncertainty, length along with its percentage uncertainty. I mean, you've got V with its percentage uncertainty, where V is the potential difference voltage. The quantities listed in table 1.2 have values that are used to calculate rho as 4.1 into 10 raised to the power minus 7 ohm meter. For this value of rho, calculate the percentage uncertainty. So using the percentage uncertainties given here, they want us to calculate the percentage uncertainty in rho. And they've given us a formula for that. We'll use a formula. Let's copy it down first so that we have it right in front of us. Here we go. Let's rearrange to make rho the subject of the equation. Rho is equals to V pi d squared upon 4 Li. To find out the percentage uncertainty in rho, you need to add the percentage uncertainties in all the quantities that basically are part of the formula, if they have an uncertainty in the first place. So if you talk about V here, let's go back to the table. In fact, let's first write down the formula and then we'll fill in the values. So percentage uncertainty in V, that is the first thing that we'll add. Pi does not have an uncertainty. It's a fixed value. It's a known quantity. So we'll omit that. Plus d squared, because of the squared sign over here, any squared power over here, any power that you have gets multiplied to the percentage uncertainty. So 2 times percentage uncertainty in D, plus 4 is a constant, has no uncertainty. L has an uncertainty, so percentage delta L plus percentage delta I. And we'll just substitute the values. So what's the percentage error in V? The percentage error in V is 3.5%. So we'll write it as 3.5 plus 2 times, what's the percentage error in D? You go back to the table, the percentage error in D is 3%. So 2 times 3 plus the percentage error in L and the percentage error in I, which is 2.5 and 2 respectively. So plus 2.5 plus 2. You add these up and you get 14%. This is the total percentage uncertainty. Now, part 2 says calculate the absolute uncertainty. What's the absolute error in this calculated value of rho? So we know the error is 14% of whatever this value is. So you need to find out 14% of that value. So 4.1 into 10 raised to the power minus 7 times 14%. So 14 upon 100, which I believe is equal to 6 times 10 raised to the power minus 8 ohm meter. 6 into 10 raised to the power minus 8 ohm meter. Is this clear? Isn't it 12%? Is it 12%? 2 2s are 4, 4 plus 2 6, 6 plus 2.5 is 8.5, 9 and 3 12. Yes, it is 12%. My bad. Let me double check. So this is 12%. Thank you for pointing this out, Abdullah. So 12%, that's the percentage error. And if you talk about the absolute uncertainty, it's 4.1. I'll have to double check. Exponent minus 7 into 12%. So this is also equal to 4.92 into 10 raised to the power minus 8. And not 6 into 10 raised to the power. Oh, yes. This is where the problem is. Harsh, I was right, but this is where I made a mistake. This should be 14 because this value here is not 2, this is 3 instead. So let's replace this. This is 3. If this is 3, this automatically becomes 14. If this is 14, this becomes 5.74 into 10 raised to the power minus 8. So I made a mistake here that basically gave us that's why you thought it's 12%. So 5.74 into 10 raised to the power minus 8. Errors are absolute uncertainties are always rounded off to one significant figure. That's why we're writing it as 6 into 10 raised to the power minus 8. And if they ask us to write the value of rho along with its uncertainty, this is how we'll write it. We'll say 4.1 plus minus 0.6 into 10 raised to the power minus 7. What I've done here is I've changed 6 into 10 raised to the power minus 8 into 0.6 into 10 raised to the power minus 7, because this is in terms of 10 raised to the power minus 7. Or what you could have done is change this into 41 into 10 raised to the power minus 8. You could have done this too and write it as 41 plus minus 6 into 10 raised to the power minus 8. So this is sorted. Thank you for pointing that out. Moving on to question number 2. A question from electric fields, which is not part of the syllabus anymore. So we'll skip this. This has been shifted to the A2 syllabus. So we'll ignore question number 2 altogether. Question number 3. Define power. What's power? Power is defined as the work done per unit time. Yes. Work done upon time or work done per unit time. That's the definition of power. A car of mass 1700 kilogram moves in a straight line along a slope that is at an angle theta to the horizontal as shown in figure 3.1. The car moves at a constant velocity for a distance of 25 meters from point A to point B. Air resistance and friction provide a total resistive force of 440 newtons that opposes the motion of the car. For the movement of the car from A to B, state the change in kinetic energy. Now, whenever there's a question that starts off with state, they don't expect you to perform a calculation. The answer is either obvious or it's given somewhere in the question. It's one of the values given in the question. So state the change in kinetic energy. Does the kinetic energy increase or decrease? That basically depends on what happens to the speed. And they've mentioned this here, that the car travels at a constant velocity. Because the car travels at a constant velocity, the kinetic energy is constant. So the change in kinetic energy is 0 joules. 0 joules. Calculate the work done against the total resistive forces. What is the work done against the total resistive forces? The total resistive forces are 440 newtons, and they oppose the motion of the car. So this is the direction in which you have resistive forces opposite to the motion of the car. So the car needs to apply 440 Newton, at least 440 newtons to oppose this resistive force. And the distance moved in this direction is 25 meters. So work done, which is defined as the product of force and the distance moved in that direction. What's the force? 440 newtons times the distance, which is 25, which is equals to 1.1 into 10 raised to the power 4 joules. 440 into 25. 11,000 or 1.1 into 10 raised to the power 4 joules. Part C says the movement of the car in B from A to B causes its gravitational potential energy to increase by 4.8 exponent 4 joules. Calculate the increase in vertical height of the car for its movement. So they've given you the increase in gravitational potential energy. They've given you the mass of the car. The only thing that they're asking you to find out is the height that it gains, or the vertical height gained. Now, you will use the formula for gravitational potential energy, which is equals to mg delta h, or change in height. The increase in gravitational potential energy is 4.8 into 10 raised to the power 4. The mass of the car, as given in the question, is 1700 times 9.81 times h, which is the height. The value that you get is h is equals to 2.878 meters, rounded off to significant figures is 2.9 meters. The angle theta. What is the angle theta? Now, a lot of students have trouble figuring out what's happening here. How do you find out the angle theta? How do you do that? So the car actually moves in this direction, up the slope. This is point A, this is point B. And this from A to B is 25 meters, as given in the question. From A to B, this is 25 meters. And this here is the horizontal. And the height that it gains when it moves from A to B is 2.878 meters, or 2.88 meters. They're asking you for this angle theta. If it moves 25 meters up, it gains a height of 2.878 meters, or 2.9 meters. What is this angle theta? So a simple question on trigonometry. Sine theta is equals to perpendicular, or opposite, over hypotenuse. So theta is equals to sine inverse perpendicular, which is 2.88 or 2.878 or 2.9 upon the hypotenuse, which is 25. the answer that you get for this is 6.7 degrees. Part D says, the engine of the car in B produces an output power of 1.7 into 10 raised to the power 4 watts to move the car along the slope. Calculate the time taken for the car to move from A to B. Now, they've given us the output power. They want us to calculate time. If somehow we can calculate the total energy produced by the car or the total work done by the car, if somehow we can do that, we can easily find out the time. So before we do that, let's go back to the question and see what's happening. So the engine produces some energy, or it produces some power. Some of that energy is used to do work against the resistive force. Some of the energy produced by the engine, part of it, in fact, 1.1 into 10 raised to the power 4 joules of it, is used to do work against the resistive forces. The remaining energy gets converted into gravitational potential energy, 4.8 into 10 to the power 4 joules. If the car would have experienced an increase in speed, we'd also consider that. We'd say some of it is also used to increase the kinetic energy, but that is not the case. So the total energy that is produced by the engine, or the total work done by the engine, is basically the sum of the gravitational potential energy and the work done against the resistive forces. 5.9 into 10 raised to the power 4 joules. That is the total energy produced by the engine. To find out time, we'll use the formula power is equals to energy over time, or work done upon time. The power is 1.7 into 10 raised to the power 4. The energy is 5.9 into 10 raised to the power 4 divided by the time. And you'll get a value for time. The answer is 3.47 seconds. Rounded off, it's 3.5 seconds. Can I repeat the energy part? Yes, I can. So this part was a bit tricky in the sense that they've given you the power. They wanted us to calculate the time taken, but you can only calculate time if you have the energy, the total energy produced by the engine, because they've given you the total output power. Now, how do you figure out what the total energy is? Some of the energy is used to do work against the resistive force. The remaining energy increases the gravitational potential energy of the car. So the total output energy, this is the total output energy of the car. Some of it goes to resistive forces, and the remaining energy gets converted into GPE, gravitational potential energy. So I don't have this, but I have this and this. So I simply added the two to find out what is the actual energy given by the engine or produced by the engine, which is the sum of the two. I've used that energy because that is the total energy by the engine. I've used the total output power and calculated the time. If you use any one of these energy as opposed to both these energy, you'll get an incorrect answer. Abdullah Zulfikar, clear? Question number 4. A child sits on the ground next to a remote controlled toy car. At time t is equal to 0, the car begins to move in a straight line directly away from the child. The variation with time t of the velocity of the car along the line is shown in figure 4.1. So they've given you a graph of velocity on the y-axis in meters per second against time on the x-axis in seconds. The screen's stuck. Okay. Yes, it is stuck. Give me a second. Here we go. So you're given a velocity time graph of a toy car. The car's horn continually emits sound of frequency 925 hertz between time t is equals to 0 and time t is equals to 6. The speed of the sound in air is 338 meters per second. Describe qualitatively the variation, if any, in the frequency of the sound heard by the child that was emitted from the horn from time t is equals to 0 to t is equals to 2. That's the first part. Now, this is a question on Doppler effect. There's relative motion between the car or the source of sound and the child that's sitting on the ground. One thing that they've told us is that the car begins to move in a straight line directly away from the child. So it's moving away from the child, moving away throughout. What happens to the observed frequency? What happens to the observed frequency when the sound source is moving away? When it's moving away. I believe this here was a diagram that we drew in class. There was an ambulance with a siren on top. You had a person over here, you had a person over here, and the ambulance is moving to the right. And you basically had sound waves like these. Where we notice that towards the observer, the frequency increases. Moving away from the observer, the frequency decreases. The observed frequency is lesser than the actual frequency. And between 0 and 2, what happens is that the speed is increasing. As the speed increases, the observed frequency decreases because it's moving away with a greater velocity. That's part one, decreases. From time t is equals to 4 to t is equals to 6. Now, this is confusing. Why is this confusing? Because it's still moving away. So I'll just assume values because I don't know the actual value. We'll calculate it later on. So when it's moving at a velocity of 0, where it's stationary, basically, the observed frequency is equal to the actual frequency 925. As it moves away, the observed frequency decreases. So let's say it decreases to the lowest value at this point, and that lowest value is 800. Let's make it 800 hertz. So from this point up till this point, all the way up till this point, all the way up till this point, the frequency is 800 hertz. And then the velocity starts to decrease again towards 0. What is the frequency that we will observe when it goes back to 0 meters per second, when the velocity, when the car stops again? Yes, the frequency that we observe when the car stops again is again 925 meters per second, 925 hertz, because there is no relative motion now. It's a stationary sound source. So 925. So for the observer, what happens to the frequency between t is equals to 4 and t is equal to 6? What happens to this frequency? The frequency, as you can see, it increases. Yes, the frequency increases. It hasn't increased to a value greater than the actual frequency, because this is what the problem is. If it's moving away, and we know that when it moves away, the frequency is lower than the actual value, how is it increasing? It's increasing, but it's still lower to the point where it becomes equal to the actual, but can never be greater unless the source starts moving towards the child in this case. Now, moving on, part B says, determine the frequency to 3 significant figures of the sound heard by the child that was emitted from the car horn at time t is equals to 3 seconds. At time t is equals to 3, the speed with which the vehicle is moving, with which the toy car is moving, is 12 meters per second. All we need to do is use the formula for frequency. Doppler effect, observed frequency is equals to V over V plus Vs Fs. Because it's moving away, you have a positive sign. If it was instead moving towards, you'll use a negative sign. Just plug in the values. V is the speed of sound, which in this question is 338. 338 plus Vs, the speed of the source, which is the speed of the toy car that we got from the graph, is 12 meters per second times Fs. Fs is the source frequency, the actual frequency, which is 925. So 338 divided by 338 plus 12 multiplied by 925 gives us 893.28, which is equals to 893 hertz. That's the answer. Any questions before we move on to the next part? None, I believe. Part C says, determine the time taken for the sound emitted at t is equals to 4 seconds to travel to the child. What is the time that it takes for the sound waves to travel to the child, given that they were emitted at t is equals to 4 seconds? The first thing here is to figure out how far apart the toy car is. So at t is equals to 0, the car is right next to this child. So you've got this child here, and at t is equals to 0, the toy car is right next to it. And at t is equals to 4, it's some distance away. Distance. This is where the toy car now is. So let's first find out what this distance is. How far away has the toy car traveled in these 4 seconds? How do you do that using a velocity time graph? Yes, the area under a velocity time graph gives us distance. So all we need to do is find out the area under the graph. And up till t is equals to 4. So basically, this is the area that we need to calculate. So you can either break it into 2 shapes, a triangle and a rectangle. You can either do that, or you can break it into a trapezium, half into height into sum of parallel side. I'll go with the trapezium formula. Area is equals to half times height What's the height? The height is 12. 12 times the sum of parallel sides. The sum of the parallel sides. This side is 2 from 2 till 4. The other side is 4. So 2 plus 4. So that's the total distance. And this is equals to 36 meters. This is how far apart. This is how far apart the toy car is at t is equals to 4. What do we need to do next? We need to find out how long does it take for sound waves to travel a distance of 36 meters. What formula do we use? We won't use v is equals to u plus at or v squared is equals to u squared plus 2as or s is equals to ut plus half at squared. In fact, we can, but we'll simply use speed is equals to distance upon time because sound travels at a constant speed. So speed is equals to distance upon time. The speed with which sound travels is 338 in this question. The distance we just calculated is 36 meters over time, which is an unknown here. This is equals to 0.1065, which is equals to 0.11 seconds. This is the time that it takes for sound to travel from the car to the child. Or if you use s is equals to ut plus half at squared, we know that sound travels at a constant speed, so the acceleration is 0, so this entire part gets cancelled out. So you're basically using distance is equals to speed into time, which is the same formula. 0.11 seconds. Question number 5. Question number 5 says the tube is initially fully submerged in water. The axis of the tube is kept vertical as the tube is slowly raised out of the water as shown in figure 5.1. A loudspeaker producing sound of frequency 530 Hertz is positioned at the open top end of the tube and as it is raised. The water surface inside the tube is always level with the water surface outside the tube. So this level is equals to this level. The speed of the sound in the air column in the tube is 340 meters per second. Describe a simple way that a student, without requiring any additional equipment, can detect when a stationary wave is formed in the air column as the tube is being raised. So whenever a stationary wave is formed inside any air column, what do you observe? How do you figure out that there's a stationary wave being formed? Because you can't actually see the wave being formed. But there's one way to know whether a wave is formed or not. And that is that a relatively loud sound is formed. Loud sound is heard. Whenever a stationary wave is formed, a loud sound is heard. So the speaker would produce a sound, irrespective of whether a stationary wave is formed or not. But when a stationary wave is formed, the sound is louder as compared to when it's not formed. And you've seen that in a lot of questions in which they don't tell you that a stationary wave is formed. They'll instead use a loud sound is first heard, or two loud sounds are heard at this in this interval. That basically means that at those points, a stationary wave was formed. Part B says, determine the height of the top end of the tube above the surface of the water when a stationary wave is first produced in the tube, assuming that an antinode is formed level with the top of a tube. Now, first thing first, we need the wavelength of sound. We've got the frequency, we've got the speed. We can find out the wavelength. V is equals to f lambda. The speed is 340. The frequency is 530 times lambda, 340 divided by 530. And the wavelength comes out to be 0.6415 basically. So lambda is equal to 0.64 meters. Now, when you get the first loud sound, can someone here tell me how many waves are formed? When the first loud sound is heard, in this case, it's an open end and a closed end. The bottom part is closed, the top side is open. When the first loud sound is heard, you'll have the bare minimum. The bare minimum is a node at the closed end and an antinode at the open end. You can't have less than that. You'll obviously need an antinode over here and a node over here. So a node and an antinode, no, this is what you will get. This is the type of wave that you'll get. We know that node to node is half a wavelength. So node to antinode, which is between two nodes, is quarter of a wavelength. So you'll only have quarter of a wavelength. 0.25 lambda. This is when the first loud sound is heard. Because this is when the first loud sound is heard, the length of the tube. Now, if I ask you, what is the length of this tube? You'll say, let's find out what's the length of a quarter wave, and that is equal to the length of the tube. So 1/4 multiplied by the wavelength 0.64, which is 0.16 meters. Do you guys get it? Why do we have quarter of a wavelength? Abdullah, Khadija. And not half, because half means node to node or antinode to antinode. Node to node in case you've got two closed ends, or antinode to antinode in case you've got two open ends. But that's not the case here. Determine the distance moved by the tube between the positions at which the first and the second stationary waves are formed. So for the first one, we already know it's quarter of a wavelength. Can someone tell me for the second one, how many wavelengths will we have? So this is the first one. In fact, let's have it this way. This here is our water surface. And this is the first loud sound. For the first loud sound, as we discussed earlier, there's a node here, an antinode here, you get quarter of a wavelength. For the second loud sound, while we pull it out, or as we pull it out, once again, you need a node over here and you need an antinode over here. You'll have something like this. A node, antinode, node, and then an antinode. That's the next loud sound as you pull it out. This is half a wavelength. This is quarter of a wavelength. And the question is, how much distance has the tube moved? So the tube started over here and it moved half a wavelength. It was initially quarter of a wavelength out. And now it quarter of a wavelength out. and then it has moved half a wavelength out, a total of 0.75, as you said. The difference is 0.5 lambda. That is how much it has moved further out. So 0.5 times whatever the wavelength was, which is 0.64, and you get 0.32 meters. That is our answer. It's a 1 mark question. You don't even need the diagram, I believe. I hope this is clear. I'll move on to question 6 now. Question number 6 says a cell of EMF 0.48 volts is connected to a metal wire X as shown in figure 6.1. The cell has internal resistance. The current in the cell is 0.8 amperes. Wire X has length 3 meters, cross-sectional area 1.3 into 10 raised to the power minus 7. So these are the important values given here. You've got the current in the cell, you've got the EMF, you've got the length of this wire, you've got the cross-sectional area, and you've got the resistance. Calculate the charge passing through the cell in a time of 7.5 minutes. How much charge passes through the cell? They've given you the current and they've given you the time. So you need to use the formula for charge. Q is equals to IT. What's the current in the cell? The current in the cell is 0.8. What is the time duration for which they want the charge? 7.5 minutes, but you need to convert this into seconds, so multiply it by 60. So 0.8 times 7.5 times 60, which is equals to exactly 360 coulombs. Part B says calculate the percentage efficiency with which the cell supplies power to wire X. What is the efficiency with which this cell here supplies power to wire X? Now, before we talk about this, I want you to understand that if the cell did not have an internal resistance, if this was not present, the cell would be 100% efficient. Why? Because the entire potential or the entire EMF or whatever is provided, the energy provided by the cell is transferred to this wire, because these connecting wires have no resistance, there is no internal resistance. In this case, the problem is that there's energy loss or power loss due to this internal resistance. So to calculate the efficiency, the first step is to calculate how much power is lost inside this resistor. And we can do this. How do we do this? We need to find out the output power. We need to find out the input power, and that will give us the efficiency. So what's the output power? The output power is basically the power that our resistor here gets. This resistor, this is the actual output. This resistor gets power is equals to I squared R. What is the current through this resistor? The current through this resistor is 0.8 squared. What is the resistance of this resistor? The resistance of this resistor is 0.4 ohms. So that is the output power, which is equals to 0.8 squared times 0.4, 0.25. You need to then find out how much power is, what is the total power given by this cell? The total power given by this cell is power is equals to VI. What is the V in this case is the EMF of the cell. The EMF of the cell is 0.48. The current given off by the cell, or the current produced by the battery, is 0.8. So 0.48 times 0.8, 0.384 watts. So this is the actual output power. This is the total power produced by the battery. And if I ask you what's the power loss, you simply subtract the two values. Now for efficiency, what do you need? For efficiency, in fact, for percentage efficiency in this case, for efficiency, you need the output power, 0.256, upon the input power, 0.384 times 100. Output over input multiplied by 100, which is equals to 67%. That's the efficiency. Is this clear? Okay. There are 3.2 into 10 raised to the power free electrons contained in the volume of wire X. So for the given volume, it's not per unit volume, it's for the given volume. These are the total number of electrons. They're asking you for the number density n of the free electrons. Basically, what are the number of electrons per unit volume? So you have the total number of electrons. You need to divide that by the volume of the wire, and you'll get the number density, or the number of electrons per unit volume. So 3.2 into 10 raised to the power 22, divide by the volume. Let's see, what do we have here? We've got the cross-sectional area in meter squared. You've got the area, or you've got the length in meter. Area multiplied by length gives you the volume. So 3.2 into 10 raised to the power 22 divided by area multiplied by length. And the number density comes out to be 8.2 into 10 raised to the power 28 per meter cube. These are the number of electrons that you will find in 1 meter cube of this wire. The average drift speed of the free electrons. So when they talk about drift speed, they want us to use that specific formula. I is equals to NAVE or NAVQ, where I is the current, which is 0.8. N is the number of electrons per unit volume, or the number density, 8.2 into 10 raised to the power 28. A is the cross-sectional area of the wire, 1.3 into 10 raised to the power minus 7. V is the drift velocity, or the drift speed. E is the charge of an electron, 1.6 into 10 raised to the power minus 19 coulombs. You rearrange, make V the subject of this formula, and solve for V. And that gives us V is equals to 4.7 into 10 raised to the power minus 4 meters per second. I'm assuming you guys are getting this. Since I'm not getting any questions from your side, I'm hoping you understand this. Clear? Perfect. Yes. Now, this is a good question. Let's see. A wire Y has the same cross-sectional area as wire X and is made of the same metal. Wire Y is longer than wire X. So wire X in the circuit is now replaced by wire Y. Assume that the wire Y has the same temperature as wire X. State and explain whether the average drift speed of the free electrons in wire Y is greater than, the same as, or less than that in wire X. So let's write down the formula. I is equals to A N V E or VQ, or V is equals to I over A N E. We're talking about the drift speed. Now, the first part here is current. But current depends on the resistance. Wire Y, same cross section area. So that does not change the resistance. Same metal, which means same resistivity. So no change in resistance. But wire Y is longer than wire X. So the formula R is equal to rho L over A. A is constant, rho is constant, L is greater. Because L is greater, the wire is longer. That means wire Y has a greater resistance than wire X. Because wire Y has a greater resistance, we know that the current depends on the EMF divided by the total resistance. So the resistance of wire Y has increased. So the total resistance of the circuit has increased. And because the total resistance of the circuit has increased, the current decreases, which causes the current, thus current in the wire or current in the circuit, and hence the wire decreases. We still haven't answered the question. We've given the reasons, but we still haven't answered what happens to the drift speed. So let's see. Let's ignore current for the timing. Let's talk about the other variables here. E is constant, so we'll ignore that. N is constant, number of electrons per unit volume. Why? Because it's made of the same material. Cross-sectional area is constant. So current determines what happens to the drift speed. Now the current has decreased because drift velocity or drift speed is directly proportional to the current. When the current decreases, the drift speed decreases. So the average, as they've mentioned here, the average drift speed is less than in wire X. The average drift speed in Y is in wire Y is less than the average drift speed in wire X because the current has decreased, and this current decreased because the resistance has increased. So that's the answer. Moving on to the last question, question number 7. Just a second. Question number 7 says, a stationary nucleus P of mass 243U decays by emitting an alpha particle of mass 4U to form a different nucleus Q as illustrated in figure 7.1. The initial speed of the alpha particle is 1.6 into 10 raised to the power minus 7 meters per second. Use the principle of conservation of momentum to explain why the initial velocities of nucleus Q and the alpha particle must be in opposite direction. Now this here is a pretty simple question. Why is it that the velocities they need to be in exactly opposite direction? You cannot have a velocity like this and like this. You can't have both velocities, both speeds in the same direction. Or you can't have them at a random angle, they need to be in the exact opposite direction. And why is that? The reason behind that, and they've given you a hint, principle of conservation of momentum. So this nucleus is stationary. Because this nucleus is stationary, if I ask you, what is the momentum of this nucleus? Momentum of nucleus P is 0. Why? Because it is stationary. So this is where you start off, which means that the total momentum after decay, because the total initial momentum is 0, the total momentum after decay should also be 0. Thus, the velocities should be in, or the velocities have to be in opposite direction. Velocity slash momentum. If they have momentum in the opposite direction, velocities in the opposite direction, they'll obviously have momentum in the opposite direction too. Should be in opposite directions. Determine the initial speed v of nucleus Q. What is the initial speed v of nucleus Q? So to calculate the initial speed v, I need to calculate, the first thing that I need to do is calculate the mass of nucleus Q. I have the mass of P, which is 243 U. I have the mass of alpha particle, which is 4U. Simple maths, 243U minus 4U, which is equals to 239U. So the mass of nucleus Q is 239U. Now that I have the mass of nucleus Q, I can use that and the principle of conservation of momentum to calculate the velocity. Pi, the initial momentum, should be equal to the final momentum. The initial momentum is 243U times 0, hence 0, is equals to final momentum, which is equals to 239U times V plus 4U times minus 1.6 into 10 raised to the power minus 7. One of these need to be negative. You either have V as negative or you'll have this as negative. If you take right as positive, this becomes positive, this becomes negative. If you take left as positive, this becomes positive, this becomes negative. But they're in opposite direction. They need to have opposite polarities. So you get 239U times V is equals to 4U times 1.6 into 10 raised to the power minus 7. This is 0. I've shifted this to the other side. I've got both these positive values. I don't need to plug in the value of U because it cancels out eventually. I'll simply solve for V. The value of V is 2.7. Sorry, this is 1.6 into 10 raised to the power 7 and not minus 7. This here was 7. This here is also 7. 2.7 into 10 raised to the power 5. 2.7 into 10 raised to the power 5 meters per second. That's the speed V of nucleus Q. Calculate the initial kinetic energy in mega electron volts of the alpha particle. So they're basically testing whether you know how to convert joules into mega electron volts, because calculating the kinetic energy is not a problem. So EK is equals to half mv squared, half times mass, which is 4U. This time around, because we need the answer in U, we need to plug in the value of U. which is 1.66 into 10 raised to the power minus 27 times v squared, the speed with which the alpha particle was moving, which is 1.6 into 10 raised to the power minus 7 squared. Not minus 7. I don't know why I keep doing this. Why I keep writing it as minus 7. It's 1.6 into 10 raised to the power 7 meters per second. And that gives us the kinetic energy in joules, 8.5 into 10 raised to the power minus 13 joules. Once I figure this out, there's only one conversion that I need to do: mega electron volts to joules, joules to mega electron volts. 1 mega electron volt is equals to mega, which is 10 to the power 6, multiplied by electron, which is 1.6 into 10 to the power minus 19. So basically 1.6 into 10 raised to the power minus 13 when you multiply the two numbers, mega and charge of an electron. How many mega electron volts will be 8.5 into 10 to the power minus 13 joules? And the answer that we get is 5.3 mega electron volts. Simple cross multiplication, unitary method. 8.5 divided by 1.6, 5.3125. So 5.3 mega electron volts. That's the kinetic energy. They may ask you to calculate the kinetic energy in electron volts as opposed to mega electron volts. In that case, this becomes 1.6 into 10 raised to the power minus 19 as opposed to minus 13. How did I get 1.66 into 10 raised to the power minus 27? So you need to understand that this mass here, 239U or 4U, does not mean kilogram. U is unified atomic mass. 1/12 the mass of carbon 12. So one hydrogen atom is 1U. One carbon atom is 12U. And how did I get it? I'll go back to the data sheet. Here we go. I'm hoping you will remember this in the exam. You won't need the data sheet, but 1U is equal to 1.66 into 10 raised to the power minus 27 kilograms. No problem. Go back to the question. Okay. So 53 mega electron volt. Part D says, a graph of number of neutrons N against the proton number Z is shown in figure 7.2. The graph shows a cross that represents nucleus P. It's some nucleus P with 148 neutrons and 95 protons. A nucleus R has a nucleon number 242. So the nucleon number is 242 and is an isotope of nucleus P. So if it is an isotope of a nucleus P, what does nucleus P and nucleus R have in common? What number do they have in common if they're isotopes? So let's write down R here. Yes, they have the same proton number. So R should have the same proton number. The proton number is equal to 95. And I can use that to calculate the neutron number. The neutron number will be 242 minus 95. 242 minus 95. 147. 147. Same proton number. Nuclear R decays by emitting a beta minus particle to form a different nucleus S. On figure 7.2, draw cross to represent nucleus R. Label this cross R. So let's do that first. R has a proton number of 95. This is where it will lie. And a neutron number of 147. So here we go. This is R. This is R. And then we need to label S. Now, some of you may be able to do this directly, but it's always safe to write down the equation given that you have the time. R is 242 and 95. It decays into S and a beta minus particle, which means this becomes 242 and this is 96. That's how the equation is balanced. So S has one more proton number. So S has 96 proton number, but it has the same nucleon numbers, which basically means that the number of neutrons that it has will decrease. So 146. So S is 96 and 146. Where is 96 and 146? This is where S is. 96, 146. State the name of the other lepton in addition to the beta minus particle that is emitted during the decay of nucleus R. So what other lepton is emitted out along with a beta minus particle? And yes, Abdullah Faraz, that is correct. An electron antineutrino or an antineutrino is always emitted out when you have a beta minus emission. In case of a beta plus, you have a neutrino or an electron neutrino. So you write anti-neutrino. Or you may write electron antineutrino for a beta along with a beta minus.